In this episode, we will see the complete details about vertical curves, such as the purpose of vertical curve, elements of vertical curve, types of vertical curve, the importance of sight distance, derivation of important formulas, the designing and setting out of a vertical curve, with a sample of calculation. We will learn everything in less than 30 minutes. Welcome to Civil Guru. These videos made in different languages, like English, Hindi, Tamil, and also in Arabic now. Please choose your desired language from our playlist. If you like this video, please like and subscribe now. On highways, when an abrupt change in the grades of vertical alignment will make a big impact on the vehicle passing over. That will lead to either injuries or dangerous to the vehicles. To avoid this danger, and to smooth out the change in a vertical motion, the vertical curves are introduced to join two intersecting grades. These vertical curves provides a smooth transition between two sloped roadways, and allow the vehicles to negotiate the change in the grades gradually, rather than a sharp cut. Thus, contributes the safety, comfort, and appearance. Before going deep into design, let us understand the elements of the vertical curve. Let us see the components of grades. The grades, or gradient of the road, is denoted as G, and it is expressed in two ways. The first one is as percentage. Example, 2% or 3% like that. And the second one is 1 in n, which is 1 vertical in n horizontals, such as 1 in 100 or 1 in 400 like that. The next component is the rate of change of grade, which is denoted as R. This rate of change of grade helps to determine the length of the vertical curve. The rate of change of grade is a constant value, which helps to produce a uniform vertical curve. For highways, it is calculated by considering the criteria of the stopping sight distance. However, the Department of Transport in every country have their own constant value based on the nature of transport in their country. Now, let us see the types of vertical curves. In principle, there are only two types of vertical curves exist. The first one is the sag curves. These sag curves are used where the change in grade is positive, such as valleys. And the second one is crest curves, also known as summit curves. These summit curves are used when the change in grade is negative, such as hills. However, while designing these vertical curves, it could be elaborated into 6 types. That is, first is a positive grade G1 is followed by a negative grade G2. Second is a negative grade G1 is followed by a positive grade G2. Third is a positive grade G1 is followed by another positive grade G2. Here we have to notice that the G2 is greater than G1. The fourth is a positive grade G1 is followed by another positive grade G2. But here, the G1 is greater than G2. And the fifth is a negative grade G1 is followed by another negative grade G2. Here, the G2 is greater than G1. And finally, the sixth is a negative grade G1 is followed by another negative grade G2. But here, the G1 is greater than G2. Now, let us see what is sight distance, and why it is considered as important in designing. While a vehicle is traveling on the road at a design speed, and there is some hazards found on the road, then the driver needs some time to observe the object and to react on it. And once the brake is applied, it will take some time to stop the vehicle, based on the deceleration of that vehicle's speed. Within these time, the vehicle will travel some distance based on the speed. The safe traveling distance between the vehicle and the hazard object is known as the stopping sight distance. In technical definitions, it is defined as: the sight distance S is the length of roadway ahead visible to the driver is the stopping sight distance. This is calculated with due consideration of 1. The time for driver to perceive the hazard. 2. The time required to react. 3. The time to stop the vehicle after brakes are applied. The minimum length required for stopping sight distances, recommended by American Association of State Highway and Transportation Officials, are given in this table. Let us take a sample on this table. When a vehicle is traveling in 100 km per hour speed, and an object is found on the road, then the vehicle needs minimum of 185 meters to stop the vehicle without any hazard. While designing, the height of the driver's eye is estimated to be 1080 millimeters. That is 3.5 feet. And the height of the object to be seen by the driver on the surface is 300 millimeters. That is 1 foot. That means, while designing, we must care that the difference in profile levels shall not be more than this limit within this sight distance. In case this difference is more than this limit, and objects are not visible within this sight distance, then we have to increase the length of vertical curve by reducing the value of the rate of change of grade, R. Hope you people understand the importance of stopping sight distance. Now, we will see how to get the length of the vertical curve, which is denoted as L. The length of the vertical curve can be obtained by dividing the algebraic difference of the two grades by the rate of change of grade, with due consideration of sign of the grades. That is, the length of curve L equals to total change of grades divided by the rate of change of grades. That is, G1 minus G2 divided by R chains. Here, the G1 minus G2 equals algebraic difference of the two grades in percentage, and R equals the rate of change of grade in percentage per chain. The standard intervals are considered as one chain. Now, we will see what type of curve can be used as vertical curve. Either a circular curve or a parabola may be used as a vertical curve. In a parabola which is having a vertical axis, the rate of change of grade is uniform throughout the vertical curve. So, the parabolic curves are used as vertical curves. Here, we have to remember our school days and recollect our memories regarding the equation of parabola. The general equation of a parabola with a vertical axis y is ax square plus bx. The slope of the curve at any point, that is, dy by dx equals 2ax plus b. And the rate of change of grade r equals to d square y by dx square. That equals 2a. And this 2a is a constant. Now, let us see what is tangent correction and how it helps to design a vertical curves. In vertical curves, all distance along the curves are measured horizontally, and all the offsets from the tangents to the curve are measured vertically. The length of the curve is its horizontal projection. Please look into this sketch carefully. In this sketch, the OX and OY is the axis of the rectangular coordinates passing through the beginning of the vertical curve, O. And OA is a tangent line having the grade of plus G1% of slope. And AB is the tangent line having the grade of minus G2% of slope. And OB is the vertical curve produced by the method of parabola. Now, let us mark a point on the curve having the coordinates of x and y, and name that point as Q. And let us draw a vertical line, PQR, through the point Q. Here, the length of PQ is the vertical distance between the tangent and the point Q on the curve. And it is known as the tangent correction of vertical curve. And it is denoted as h. Now, let us find the value of h. This h equals PR minus QR. Here, the value of PR equals G1 into x, and QR equals y. Now, PQ, that is h equals G1x minus y. Here, G1 is slope in percentage. And x is the horizontal distance, or the number of chord, n measured from the beginning of curve. Now, we will find the value of this y by using the equations of parabola. That is, y equals ax square plus bx. And dy by dx equals 2ax plus b. Now, at the beginning of curve, at point O, the value of x equals 0. In that case, dy by dx equals plus g1. We already knew that dy by dx equals 2ax plus b. Here, when the value of x equals 0, then g1 equals to dy by dx. That is equals to 2a into 0 plus b. Finally, g1 equals plus b. Let us substitute this value of b in the general equation of parabola to find the value of y. That is, y equals ax square plus bx. Here, the value of b equals g1. That means y equals ax square plus g1x. If we do the reciprocal of these values, then minus ax square equals g1x minus y. We already knew that the value of g1x minus y equals h. So, the value of h equals minus ax square. Here, a is a constant. In vertical curves design, this constant is denoted as k, so we can call this as h equals kx square. X is the horizontal distance in algebraic formulas. So, x can be replaced as n. Because n is the total number of chords with uniform intervals, counted from point O, which covers the total length of curve L. Finally, this can be marked as h equals kn square. The difference in elevation between a vertical curve and a tangent to it varies as the square of its horizontal distance from the point of tangency. This difference in elevation is known as the tangent correction. Now, we will derive a formula to find the value of k. Extend this tangent of grade g1 up to c, which is vertically above point B. Now, let us draw a horizontal line until it meets at point D in the line of BC. And let us draw one more line vertically, starting from the point of apex, A, which is passing through the middle of the curve, connecting the points F, E, G. Now, let us assume the length of the chord at uniform intervals is L. The number of chords at each side of the grade is n numbers. So, the distance between the starting point of O to the midpoint of E is n into L. That is equals nL. Similarly, from the midpoint of E to the endpoint of B also nL. So, the total length of vertical curve L equals 2 into nL. That is 2nL. And total number of chords in this vertical curve, that is n equals 2n. G1 and G2 equals grades of two tangents. And E1 and E2 equals corresponding rises or falls per chord length L. Now, let us do some algebraic calculation. That is, OA equals AC. And CD equals n into E1. That is, NE1. And BD equals minus n into E2. That is, minus NE2. Now, CB equals CD plus DB. That is, NE1 plus minus NE2. That is, n into E1 minus E2. Here, at the end of the curve, CB equals to h. We already knew that h equals kn square. Here, n equals 2n. That means kn square equals k into 2n square. That is 4kn square. Finally, CB equals 4kn square. That is equals to n into e1 minus e2. Now, k equals n e1 minus e2 divided by 4n square. Here, this n and square of the n gets cancelled. So, finally, k equals e1 minus e2 divided by 4n. In the above equation, proper care for signs must be taken while substituting the numerical values of e1 and e2. Here, we will see a sample of design calculations by using the tangent correction method. The known informations are: a parabolic vertical curve is to be set out, connecting two uniform grades of plus 0.8% and minus 1%. The chainage and the reduced level of point of intersections are 1,660 meters and 238.00 meters. It is decided to fix the pegs at uniform chord intervals of 20 meters chainage. And the rate of change of grade is 0.005%. That means the rate of change of grade for 20 meters chain is 0.005 into 20 meters. That is 0.1% per chain. First, we will calculate the total length of the curve. Already we knew that the length L equals G1 minus G2 divided by R. Here, G1 equals plus 0.8% and G2 equals minus 1%. And the rate of change of grade per chain equals 0.1%. So the length of the curve equals 1.80 divided by 0.1. That equals 18 chains. That is known as N. This equals to 18 chain into 20 meters of each chain equals 360 meters. And the length of the curve at either side of apex equals to 9 chains. And this is known as N, which is equals to 180 meters. Now, we will fix the tangent points. The chainage of intersection point is 1,660 meters. So, the chainage of first tangent point equals 1,660 meters minus 180 meters, that is equals to 1,480 meters. Similarly, the chainage of second tangent point equals 1,660 meters plus 180 meters. That is equals to 1,840 meters. Now, we will find the RL values of each tangent point. For first tangent point, the value of G1 equals 0.8%. And the length of the tangent point from the point of apex is 180 meters. So, the difference in elevation equals 1.44 meters. So, the RL of tangent 1 equals RL of intersection point 238 minus 1.44 meters. That is 236.560. Similarly, for the second tangent point, the value of G2 equals 1%. And the length of the tangent point from the point of apex is 180 meters. So, the difference in elevation equals 1% into 180 meters, that equals 1.8 meters. So, the RL of tangent 2 equals 238 minus 1.8 meters. That is 236.2 meters. Now, we will find the value of point E. That is, the average of point O and point B. That means E equals 236.56 plus 236.2 divided by 2. That equals 236.38 meters. And now, we will calculate the value of F also. since F is midway of point A and E. The RL of point F equals RL of A plus E divided by 2. That is 238 plus 236.38 divided by 2. That gives the value of 237.19 meters. Now, the apex value, that is, the difference between A and F, is 238 minus 237.19. That is 0.81 meters. Also, this is known as the H value of 0.9 from the beginning of curve. Now, we will check whether these values are correct or wrong, and also calculate the reduced level of intermediate pegs from our known derived formulas. For that, we have to find the value of constant K. To find the value of K, we have to find the value of E1 and E2. E1 is the elevation on the grade of the uniform chord of 20 meters intervals. That is, E1 equals G1 into 20 meters. That is 0.8 divided by 100 into 20, which equals 0.16 meters. Similarly, for E2, minus 1 divided by 100 into 20, that equals minus 0.20 meters. Now, we will find the value of constant K. That is, K equals E1 minus E2 divided by 4n. Here, E1 equals 0.16, E2 equals 0.2, and n equals 9 numbers. That gives the value of 0.01. That is, K equals 0.01. Now, we will find the value of H at the apex point of AF. We already knew that H equals K into n square. That means AF equals 0.01 into 9 square. That is 0.01 into 81. That gives the value of 0.81 meters. That is the tangent correction at the point of apex. If we compare this value with our previous results, both are same. That means our previous calculations and the result arrived through these formulas are correct. Now, it is time to calculate the RL value of other intermediate pegs. For that, first we have to calculate the elevation value on tangent line for every intermediate points. That is intermediate pegs. And next, we have to find the value of tangent correction, H, for every peg. And, finally, we have to deduct this tangent correction from the elevation values, which gives the value of final reduced level on the parabolic curve. Now, we will see in detail. The tangent elevation for the first peg is RL value of 0.0 plus the value of E1. That is 236.56 plus 0.16 equals 236.72. The elevation for the second peg is RL value of 0.0 plus 2 times of the value of E1. That is 236.56 plus 2 into 0.16 equals 236.88. And, similarly, for the third peg is RL value of 0.0 plus 3 times of the value of E1. That equals 237.04. Repeat the same procedure until we reach to the 18th peg. That is, the extended tangent of grade 1 until point C. Finally, the elevation value of 18th peg is RL value of 0.0 plus 18 times of the value of E1. That equals 239.44. Now, we will start calculating the tangent correction. That is, H value of every peg. The formula to calculate the H value is K into n square. Here, the K value is 0.01. So, the tangent correction of first peg is 0.01 into 1 square. That gives the value of 0.01. Next, the tangent correction for second peg is 0.01 into 2 square. That gives the value of 0.04 meters. Similarly, for peg number 3 is 0.01 into 3 square. That gives the value of 0.09 meters. That is the tangent correction for peg number 3. Repeat the same procedure until we reach to the 18th peg. Now, h value for peg number 18 is 0.01 into 18 square. That gives the value of 3.24 meters. This value is the tangent correction of 18th peg. Finally, we will start calculating the RL values on the parabolic curve. That is, value of elevation minus the tangent correction. First, we will find the RL value for first peg. That is, the elevation of peg number 1, 236.72, minus the tangent correction of first peg, 0.01. That gives the value of 236.71 meters. Next, we will find the RL value of second peg. That is, the elevation of peg 2, 236.88, minus the tangent correction 0.04. That gives the value of 236.84 meters. And now, we will find the RL value of third peg. That is, 237.04, minus 0.09. That gives the value of 236.95 meters. Repeat the same procedure until we reach to peg 18. At last, we will find the RL value of 18th peg. That is point B. We will cross-check this value with our previous results. That is, the elevation of peg 18, 239.44, minus the h of the 18th peg, 3.24. That gives the value of 236.20 meters. This value is equivalent to our previous result. That means all our calculations are perfect. This is the procedure of designing a vertical curve. Hope you people are enjoying it. If you like these videos, please subscribe now and share with your friends. And also don't forget to press the bell button. Thank you.